It is my pleasure to welcome you to the fifth part of the crash course Foundations of Quantitative Research. In this lecture, I would like to explain the logic behind inductive statistics and how you can use inductive statistics with regard to your sample size. Before I start, I need to mention that some use the terms inductive statistics and inferential statistics interchangeably. Apparently, I do not. Under inductive statistics, I will explain the relationship between sample and population, whilst under inferential statistics, I will go in all the tests, inferential statistical tests, like the t-test, the chi-square test, regression analysis, and so forth. But now, the logic of inductive statistics. Think of the population of the United Kingdom, which I believe is roughly 68 million at the moment. And we want to get some information about this population. We will not be able to collect data from all of the 68 million inhabitants of the United Kingdom. But we can collect data from a much smaller sample. Then we would like to have that our values that we have measured in our sample reflect the true values of the British population. The central question then for inductive statistics is, with what probability and margin of error do the results of our sample reflect the true values in the population? The probability with which the sample results reflect the true values in the population is called confidence level. And the range, how much our measured values are allowed to deviate from the true values in the population, is called the margin of error. You can use inductive statistics in two ways: ex ante and ex post. Ex ante, before you collect the data. Then your objective is to determine the sample size. How many participants do we need? To this end, you need to set a confidence level, the probability with which our values represent the true values in the population, and we need to define a margin of error. So how much do we allow our values to deviate from the true values in the population? And having done this, we can calculate the sample size. How many people do we need to get in our sample? After data collection, we already have the sample size. We know how many participants we had. Then we can work backwards and can calculate the confidence level and or the margin of error. So again, the confidence level is the probability with which the values of the sample represent the true values in the population. And the standard is to assume 95%. The margin of error is the deviation of the measured values from the true value in the population, the deviation that we allow. For example, 5%. I would normally say go rather in a real research project with 3%. But here I've taken 5%. Using these two assumed figures, 95% and 5% margin of error, I would like to exemplify what this means. Assume we do our study 20 times. So we throw a questionnaire out 20 times. And let's assume the true value in the population is 50%. For whatever question we're having, what party would you vote for, or something like this. 50% would say, yes, I vote for this party, and 50% would say, no, I do not vote for this party. Our measured values let's assume they're all in the columns. Like for study 1, we measured 51%, study 2, we've measured 48%, study 3, we've measured 47%. Our target range, the margin of error, is 5%. And if we have a confidence level of 95%, that means that 19 times out of our 20 studies, our margin of error, our range, will include the true value. But one time, it's 95%, is 1 out of 20, one time we will be completely off. One time, our margin of error does not include the true value. When do you need inductive statistics? Not always, and quite often in academic research, you do not really need inductive statistics. Inductive statistics are not absolutely necessary if you have a rather exploratory or explanatory research design. If you want to find out if A generally has an effect on B, you do not need inductive statistics. You do not need to calculate your sample size. Not necessarily. So for instance, I want to find out if work satisfaction generally has an effect on organizational commitment. I do not necessarily need inductive statistics. But for some surveys, you definitely need it. You need inductive statistics. And these surveys or approaches are rather descriptive, representative designs. Election polling is a good example. What candidate would you vote for if we had a general election today? Then you want your sample to represent the electorate. What is important to mention in this context? Inductive statistic does not tell you if your sample is representative. The definition of representativity is a sample is representative when the distribution of attributes of the sample resembles the distribution of attributes in the population. And this is a mistake that some make, to think, I just need a larger sample and then I have a representative survey. It's not quite true. But larger sample is of course not a bad thing, because with a larger sample, there you come into its inductive statistics. And inductive statistics can tell you what is the aforementioned confidence level and margin of error. There are multiple options to draw a representative sample if you wish to and if you need to have one. One is quota sampling. I will give you an example in a moment for quota sampling to make this clear. You recruit your participants based on a quota that represent the distribution of attributes in the population. So of course then a few attributes you need to know how they are distributed in the population. On the other hand, you have random sampling or probability sampling. In this case, every element of the population has the same chance, same probability to be selected into the sample. As I said, I would like to give you an example for quota sampling as a bit of an excursus. This example comes from a research project, and I could publish the results with 2 co-authors. It's about the relationship between organizational commitment, commitment to supervisor, and servant leadership. My co-authors and I wanted to have a sample that represents the employed population in Germany. So what we got out is, from official statistics, how many women and men are employed in Germany in certain age brackets, 20 to 35 years, 35 to 45 years, 45 to 55, and 55 to 65 years. So on this table on the left-hand side, you see the official statistics. Then I gave students in some of my lectures, I told them that they have to collect data, and they're given a quota according to the attributes female, male, and age brackets, and they had then to collect the data for this project. In the end, we came up with 1,756 participants, and now you can compare, is our sample, does it match the official statistics? And here, happy days. It's of course not entirely on point, but it's rather comparable. So you have the so the distribution in the age brackets in percent from the official statistics, and on the right you have the distribution in our sample. Then compare. We have 23.68% official statistics, and our sample 26.59. So a bit higher, but fair enough. And the next age bracket, 35 to 45 years, in the population, 24.78% on this age bracket employed, and we have 24.20%. So we're we're rather fine here. Now here, first I want to give you an idea, or wanted to explain the logic of inductive statistics. Now, how can you utilize and how do you utilize inductive statistics for determining your sample size? And you can calculate your sample size, and here you see the two equations. I will go on the next slide, I will go deeper into one of them to explain the logic behind it. You have an equation for an infinite population and for a finite population. One might say there are no infinite populations. Every population in this world is finite. And that, strictly speaking, this is correct. But there's a rule of thumb. When your sample size, lowercase n, divided by your population size, uppercase N, is smaller than 0.05, you can use the equation for sampling infinite population right away. The reason for this being is these two equations, they're identical with one exception. In the equation for finite populations, you have a correction factor in the denominator. This correction factor, in its denominator, you have the size of the population. And if the population gets very, very large, the size of the population is very large, then this correction factor, as the population size is in its denominator, gets very small and has virtually no impact on the overall term. For simplicity reasons, I would like to explain calculating the sample size with the equation for infinite populations. And this is, I should also mention, if you have a population or populations that are large enough, the population of Manchester, of London, you do not need to bother with the idea of finite populations. Then you can go straight to infinite population equation. Now, but as I said, let's jump into the equation. We have the sample size, n, z is a z value, that represents the confidence level. So the probability that our results, our values, match the true values in the population. We have p and 1 minus p. P is an assumed distribution. You there take normally 50%. That is your default approach. And then if you take 50%, it is 50% times 1 minus 50% is a 50%, 50% times 50%. In the denominator, you have delta p. And delta p is your margin of error. So what you typically do, I already set as a default option, you assume a distribution of 50%. The reason for this being that this is your worst case scenario, if you will. 50 times 50 is 2,500. 60 times 40 is 2,400. 70 times 30 is 2,100. So if you take 50 to 50, you have the largest value in the numerator. So you're on the safe side, because if the numerator goes up, n will go up. So here, then you are on the safe side. The confidence level, that is a standardized, z value is a standardized value that is related to a certain level of confidence. And the standard is to assume we're right with a probability of 95%, confidence level of 95%, and the corresponding z value is 1.96. Here again, the z value is in the numerator. If you want to have a higher probability that your values match the true value, your values from your sample match the true values in the population, you can go higher to 99%, but then the z value goes up. And the z value is in the numerator. So if that goes up, n goes up, sample size. That means you can understand this. For a higher confidence level, I buy myself through more participants. Finally, the margin of error. That is the range of, this is how much we allow our values to deviate from the true values. And the standard is 3%. So let's go this step by step. We assume we have a distribution of 50%. 50% say yes, 50% say no. We don't know this, but that's our assumption that will come out in our questionnaire. Then we put in the confidence level. And if you put in our equation 1.96, we can say our values that we have measured reflect the true values of the population with a probability of 95%. As we will never be exactly on point, we need the margin of error. We say we allow our values to deviate 3% up or down from our measured values. If we put this in the equation, then we can say from step 2, with a probability of 95%, the true values of the population are in a range of plus minus 3% of our measured values. So with the assumption of 50% measured, the true values will be somewhere between 47% and 53%. And if you put these numbers into the equation, you will come up with sample size of 1067. This is sort of a magical number in statistics and inductive statistics. And perhaps think back, if you see some political polling, what was it what you had? Brexit, Remain or Leave. You always had such numbers, a bit more than 1,000. And that's because of this magical 1067, that we can say with a probability of 95%, we're right. And our margin of error, the target range, is plus minus 3%. But you do not, assuming you have a finite population, you do not need to calculate this by your own or by hand. There are tools in the internet where you can put the numbers in and get your sample size out. This is what you do, as I said before, ex ante, before you collect your data. After you've collected your data, you already have the number of participants. And then you can solve this equation for Z, and you can determine the level of confidence. And that might change, might even get better, because you might not have measured 50%, but 30%, 20%, and then solve the equation for Z, then your level of confidence will be higher, and you can determine this after you've collected your data. This was inductive statistics. The next part is about descriptive statistics. And until then, I wish you all the best, and it is bye-bye for now.